Recording. Yeah. All right. So today we have Yufan Xu is presenting on design of a new facility that he's been working on. So this is the LEAP, Lithium Experimental Application Platform. So there is, of course, there's always been a lot of interest here at the lab on lithium-related technologies for fusion applications. And I think we're really increasing our attention on this area. As Stan Kay mentioned on Monday, as well as Steve Calley alluded to, there's some emphasis from the DOE requesting that our lab specifically start developing more plans towards developing liquid lithium technologies. And so LEAP is one possible avenue for ramping up our activities in this area. So with that, I'll go ahead and hand it off to you. All
right. Thank you, Matt, for the introduction. And today we're going to talk about LEAP, which stands for Lithium Experimental Application Platform. And indeed, as you just said, on Monday, we had an all-hands meeting, and Steve was mentioning that liquid metal has been one of the alignment that we have with the DOE strategic goals that where the PPL is heading. So today, I'm basically going to very swiftly go over some of the points here. That first of all, why do we need this large-scale lithium experimental platform? And then I can talk about the recent developments of and design of the LEAP. And also in the end, probably want to discuss a little bit about how it can be an interface to a fusion facility.
You've got a title on your slide that we're not getting to see.
Okay. So that's probably my screen. Second. Thank you. Let's see.
It's not that much better.
If I can hide it.
I think you also need to press OK.
Just hit OK on this meeting is being recorded. I think that'll.
Oh. Okay.
Let's get rid of that. Let's get rid of that thing.
Yeah, that thing is.
So high floating meeting controls.
Yeah. Sorry, where?
Yeah.
High floating meeting controls. Yes. Boom.
There we go.
Control Alt Shift, like 60 different keys.
Now it seems like the bottom's cut off, to be frank.
Oh yeah, there's still the menu at the bottom. I think that's all right. We can just the logos.
Oh, there we go.
Perfect.
Perfect. Thank you. And also, if you have any questions, I prefer you can leave it in the to the end of the talk. That will be roughly about 40 minutes. But if you have questions for clarifications, just let me know. Okay. So this is one of the slides we already seen on Monday that taming interactions between plasma and the reactor wall is one of the missions that the PPL here has. And then this is a part of how we want to develop this technology and knowledge to advance the engineering about the fusion device and fusion reactors. And also, we recently have submitted this FIRE Fusion Innovative Research Engine Collaborative Proposal. So all these are pushing towards more attentions on the liquid metal development at PPL. So this whole thing is kind of motivated by the liquid lithium being very special and very beneficial things for plasma confinement. And in the past research that's done here at PPL, for example, I'm showing here on the left where the energy confinement time, where you see a very one of the best case has been done with the lithium enhanced pedestal H mode, where the red circle is on an STX. And if you're on the right side, there's LTX beta, which is the very exciting device that here at PPL, where you see the flattened profile of the electron temperature. So this suggesting a very novel approach of the low recycling regimes, which is also very promising for increase and greatly enhance the confinement ability of the plasma. So all these are related to we have a lithium-coated wall. And as a fact that liquid lithium has been proposed to be an important concept as plasma-facing components, which it has a lot of benefits, include, it's a low Z, and it can gather some impurities from plasma, enter this low recycling regimes. It can self-healing, especially we are facing a lot of wall damage with the extreme particle and heat flux. And last but not the least, that with the flowing lithium, you can also enhance the heat transfer at the diverter or limiter regions. So on the right side, I'm showing one of the schematic taken from I think Andre's one of the Andre's talk, where you have this is one of the proposals that we are putting a row of liquid lithium diverter tiles at the bottom. This is the top down view where at this regions we're expecting magnetic fields around 1 Tesla and a very high heat flux, 10 to 100 megawatts per meter square. So, but however, we do have a lot of challenges facing to this concept. And one of those has been the fluid stability. So I'm just showing here one of the earlier concept that we had where you flow lithium, from the center stack all the way to the catch basins. And this basically have lithium everywhere, have a larger surface area. But however, people found out it has, the lithium stability has to do with the, the land scales and how much lithium you can pull as a surface area. And in addition, we're also facing challenges of how do we circulate lithium and lithium hydride, and also how do we plumb, the systems. We need to have a reliable and large scale, safe plumbing system for all the lithium's input and output. Also, we're facing another challenge about lithium is that it's a alkaline metal, which has a reaction with liquid waters and all nitrogens and a lot of other chemicals that raise the safety concerns and maybe increase the erosions or corrosion issues. So here I'm circling back to one of the issues that we're facing is that the surface instability. So when you have an open surface lithium, liquid lithium, either it's on the tile or on some flowing channel, you have to be careful about the size and the scales that you're choosing, because just from the J cross B force, the Lorentz force, right, the plasma currents and the B field, you can generate this forcing that can eject the lithium into the plasma, which is not desirable. And you can see from the bottom of the slides where you have, this is the lithium in a cup experiment that has been conducted on D3D a while ago. And this is one of the plasma facing components, the DIME device. And you probably can see the post-exposure photo where the lithium actually exits the little reservoir and got ejected into the plasma. So on the right side, this is one of the paper by Mike Jaworski back in et al. Back in 2013. That you see these regions of stable, unstable. This is mostly from the Rayleigh-Taylor instability. That you can see there's a stability curve that we have to be careful about. If you have a larger porous or droplet size, then it's more prone to the unstable regions on the right corner where the gray corner is. So that's why we have to think about how large and what is the land scale that we can do with the free surface, lithium as plasma facing components. And of course, why we don't see such a very violent injection events at the NSTXLD is because the scale is on the left side of the curve, as you can see. So what is the physics behind this? Just very briefly, we can list the growth rate from the linear analysis of all the forcing components here. For example, we have the first two terms that's relatively, that's correlate to the gravity and body force induced by the J cross B. And this is what the Rayleigh-Taylor like. If you have lithium and plasma, and then one is intruding to the other, and you generate this unstable surface interface. And you have this negative terms in the growth rate, right? This correlates to a stabilizations due to the surface tension. And the last term, you can see the relative velocity differences between the lithium and plasma give you this destabilizations of Kelvin-Humboldt's instability, just like the clouds that we see, sometimes you have this wave. So just keep in mind that when the imaginary part of this growth rate is larger than 1, the wave becomes unstable and you're facing ejection events. And also important thing from this equation you can see is the only negative term or only stabilization term relies on the surface tension. Okay.
So if you just go back, where's the magnetic field in this?
It's the this F lithium. F lithium includes the J cross B force.
So that's the J cross B force that Jaworski was evaluating.
That's right.
Okay.
Yeah. Yeah. So I think for this curve, it doesn't include the last term, which is the Kelvin-Humboldt's instability, but the first three terms. Okay. Okay. So that being said, there are alternative to this liquid lithium plasma phasing components. First of all, we can have a simplified lithium vapor box that doesn't have a flowing surface or expose the lithium surface. Or you can have a capillary porous system or CPS with the flow. And then, of course, in the end, we can have a smaller scale, right? Instead of a large surface area, you can have a smaller scale like divergulates where the flow goes up and down instead of across the magnetic fields. And also you have limit, which is these trenches that are powered by the thermoelectricity. Okay, so when you have a thermal gradients in these tiles, it generates induced currents. So I won't go into details of all these LM PFC designs, but I will just put it there that we need to prototype and we need to test all those subcomponent designs. And currently we have a lot of simulations, but eventually we want to do experiments and then to verify a lot of the concept that we're developing. Okay, the second largest challenge we're facing is the circulation of lithium hydride mixture. So I'm here is just drawing one of the concept here that's adapted from Ono et al. 2017. But what I did in addition is I put it, there's a little, I'm sorry, give me 1 second. I put this in situ MHD centrifuge here. What does it mean is, if you have a diverter that has a flowing liquid lithium and there's retentions in the deuterium and tritiums, we will be able to recycle them through this a loop that you can take the deuterium and tritiums from the diverter regions and then use the centrifuge to separate them or concentrate some of the lithium hydrides. And eventually this goes to the distillations columns and then the species separators and go back to the plasma through this DT refuelings. But some of the basic estimates for this lithium hydride separation requires a volumetric flows about 1 liter per second for the minimum of the tritium recycling. And also for all the fast flows, right? For example, CPS lid with a flowing ducts, you also requires very extremely fast flows, about 1 to 10 milli per seconds, if not more. So all these requires that you have a large quantity and also requires higher lithium mass flows in parallel of all the system. And this is no matter what design you have, we have to think about how do you pump lithium in and out the system. And this is something that has to go with all the designs, no matter what we go in the end. Okay, so another issue that we're facing here is because the liquid metal has a high electric conductivity, so it's facing a significant MHD drag. So the B field, the magnetic fields in the tokamak will acting as a brake, like magnetic brakes, acting backs on the flows. The higher speed you have, the higher drags you will be facing. And then some of the solutions including use insulating pipings or developing some of the magnetic field shielding pipings and also apply external currents to drive the flow. So all these has to be tested and in order to develop some sort of a prototype and then to verify the concept actually works. Okay, so the last but not least, of course, the last challenge of the liquid metal PFCs that we're having today is lithium safety. And one of the things we really want to spearhead and push it forward is how do we develop a safe system that can operate all these at the lab? So first of all, let's know our enemies, right? So what is lithium? And how does the lithium react with different chemicals? So lithium, first of all, is reactive with water and air, especially moisture air. And you can see these are the exothermal reactions that release about 243 kilojoules per mole. It also reacts with nitrogens, and it forms, if you look at the videos on the right, the first one is reaction with water. It bubbles a little bit and it floats around. It's not really very dangerous looking. And on the bottom, you see this slightly changing color over 1 minute, right? From shiny to this gray color. That's the reaction with nitrogen. So all these react pretty fast. And the reaction is catalyzed by the presence of moisture in the air. Lithium with oxygens, this will burn, but just giving you a reference, it will probably be giving out the same heat as burning a firewood. It's on the same order of magnitude. So lithium is incompatible with moisture, oxygen, nitrogen. And that's why we have to require a working environment that doesn't have too much of the impurities, including this moisture, oxygen, nitrogens, to guarantee the safety. Also, ignition's temperature in the air for lithium vary from 180 degrees C to 640, depends on surrounding conditions. And the reaction, of course, is, again, sensitive to this moisture and other impurities. Solid lithium, however, at the room temperature is not considered paraphoric, which means it's not going to burn on itself. And except for lithium powder, which is, powder in general has different hazards. For example, because they have a much higher surface area. Molten lithium is considered to be paraphoric, so if you're not handled correctly, it could be dangerous. So here's one of the things that we all wanted to remember is that there was a lithium incident in Sandia National Lab back in 2011, where the helium heat exchanger failures leads to a hydrogen explosion. And this is from the papers published in 2021, analyzed that there is a liquid metal embrittlement that in the mild steel they're using as a chamber. So that brings attention that we have to be careful to select the materials to work with lithium. And of course, what happened afterwards is that these liquid lithium sprayed onto a pipe holding the coolants, which is water. So all these unfortunate, chain reactions leads to the incidents that requires that we have to build a robust system designed to mitigate the potential hazards and separate them if possible. Okay, so these.
Just one quick
Yes.
comment.
Yeah.
The lithium actually sprayed onto a water-cooled ceramic break. And so that immediately cracked and let water into the system. It wasn't a metallic cooling pipe. It was a
Don't use
ceramic break. Yeah.
Don't use ceramic.
Use ceramic.
Anything porous that can trap moistures or anything, don't use it. So larger lithium mass experimental platform is thus, hopefully I can convince you that needed for the liquid metal PFC prototyping. And we're facing three major challenges. And these design principles should include the counter solutions for all these challenges. So first of all, if we want to prototyping different liquid lithium PFCs that range from vapor box to a fast flow to divergelets, we have to design this platform be flexible and versatile. And second of all, we have to make sure that we have this lithium inventory can get to a much larger quantity. And currently, we have about 5 pound limit in the lithium labs at PPL. And it's not being, it's not something people haven't done before. And for example, expert from Argonne National Labs and also EFRIC from the Michigan State. They all been working with much larger lithium quantities, of course, for other applications. In the end, of course, we have to build this robust safety features and protocols to ensure and guarantee that everything work here is very safe and up to code. And also, we have a national safety guidance guidelines to follow. Okay. All right. So then we come with this club room solutions. And just to put in a nutshell, I'm showing here on the left is the very simple schematic drawings of how the glove room going to look like. It's basically a human-sized glove box. What you can do is you can put your hands into these windows, which I didn't put the gloves there, but you can see from the manufacturer samples that you can operate and then changing some of the valves and push some buttons. But mostly the experiments or the circulations will be done automatically from the outside. And the good thing about this is you can, because we're doing, remember, we have to be versatile and flexible. So we have to kind of change the experimental device from time to time. And it won't be possible if you have just normal sized glove box. And especially if you have like permanent magnets or magnetic coils that's large in size. And also you have to enter, right, the box to do the operations. So that's why we designed this very flexible and modularized glove rooms. So this is to test the full sections of fast-blowing lithium system and with the heat source and B field. This is right now in planning phase, and we have completed the final design review for the glove box. The central components is a 2 meter times 3 meter times 2 meter prefabricated modularized glove box. So when I say modularized, it actually means all the panels you see on the schematic is removable, and you can change into different shapes. You can put different penetrations. You can design different geometries. You can expand it, or you can change the size of it. It's just like a Lego set. But of course, it's a stainless steel Lego set, and it can handle up to 50 pounds of lithium. It will be led by PPL. It will be probably the largest working liquid lithium fusion experiment in US once built. So the key things here to guarantee the safety is that we purge argon during these operations when the door is closed, that to keep the moisture and oxygen level below 1,000 ppm, which is empirically been proven that is sufficient for this secondary confinement. Right, because all the lithium will be inside this first stainless steel pipe, and the box is to exist there to ensure the safety if there's any leaking or any hazardous events. Okay. Yeah, of course, we have equip the gloves and quick open doors. So whenever we decide between the experiments, we have to open the door, we have to replace the air or the argon inside the glove box with room air. And once the oxygen level reached a certain level and safety level, then you can open the door. So the lock will be controlled and connected to the oxygen monitor. Okay, so this is a brief overview of the LEAP system. As you can see, what I'm showing here for the box is the LEAP facility, and this is the one that has passed the FDR. On the right side is what inside the box. And we are currently working on the design review for this. And you can see it's mainly composed of a glove room, cleaning system, and storage and transfer. So we have solutions for all of these. And if you're interested, I can send you some slides and information about this. And I won't go into detail into each component. So let's talk about the design choice. Why do we arrive this? Why can't we just have a lithium loop in the air, right? So it turns out there are many different varieties of a lithium loop already existed. Just in US, we have this, for example, lithium loop in mean, which is one of the devices at UIUC. We have sodium loop at Argonne National Lab. We have sodium loop in UW-Madison, and also Michigan State. They have a lithium scraping system, and this is FRIB. So what is the optimal secondary enclosure design for LEAP? I'm going to go over very quickly about these design choices. So we listed and studied each single of these scenarios where you can have one layer or second layer of confinement, whether it's exposed to the room air what is the way to get rid of the smokes and fires. For example, if you can see on the second and third, there's a water tank attached to it. This is the wet scrubbing system that developed at Argonne National Lab. In fact, their whole building is attached to a water tower that can scrape any smokes and fire in case there's incidents happen inside the building. Of course, you can think about that. You have to spend a lot of resources in facility development. And if it's small quantity, you can have filter system, as I listed it over there with the white squares. And in the end, you can purge the whole secondary confinement with argon, so to make sure it's airtight. And the way to approach this is we listed all the the hazard levels. This is probably taken inspiration from our ESH. That what happened when you have a full exposure of all these hazards, and what is the hazard level for all of this? For example, if you have room air and just one layer of confinement, right? The full exposure when the hydrogen fails, when you have in contact of water, it generates hydrogen. That's pretty higher likabilities and probabilities than, for example, if you have a secondary confinement. And also you can have fires, smokes, and in this system, you won't be able to get rid of them. And that's sustained to be a pretty large factors. Of course, on the upside is that this requires very low facility complexity. So imagine you have a very complex system with all the controls and knobs and monitors. That will give you a lot of more hazard because when you operate this, the level of complexity increases. That you have to follow different steps of protocol, and that ends up actually being less safe because you have to remember everything. The system has to work perfect all the time. So simplicity is actually a plus here. So in comparison, you can see here the web scrubber system is a little bit better at making sure there's no hydrogen accumulations. And then there's no asphyxiations. The fire for the smoke, although it can still generate them, but it's probably under control. But it requires pretty high facility complexity, which means you have to install all the ventilations, you have to remodify the building, and including very prompt hydrogen detectors. So in the end, this is one of the strategy that FRIBs at Michigan State University use. Where you use very limited, you have this secondary confinement and then make sure it's airtight, and you fill the air with argon, which means there won't be any, there will be small quantity of moistures and oxygen, but nothing to be dangerous that lithium can react with. So you get rid of all this, hazard with hydrogens, fires, smokes. However, because it's not room air, you do face a very low hazardous of asphyxiations, which means deplete of oxygens. But as long as you can operate this and make sure the box is not leaking, and when you enter it, make sure there's enough oxygen in the room, that shouldn't be an issue. Okay, and this doesn't require modification of the whole building, of course. So in the end, we think this is the optimal design. And as I can see, we come up with all this index for facility. The more complex, the higher facility index it is, the more dangerous, right? The higher hazard index it is. And you can make this a little cute contour plot. Of course, all the numbers are sort of arbitrary, but if you change it roughly, it's on a qualitatively comparison. You can see that 708, which is the argon fused the secondary confinement, indeed in the lighter color zone, which means it's the preferable choice for the design. Okay. So this ensures the safety working with the molten lithium. Complexity of facility involved with the design will be less than the other ones. And then, operation and procedure will be relatively simple. So that's how we decide to use the glove room solutions. And I'm here is to show you a little concept of what the lab will probably look like. And I put a human there so you can see the size of the box and some relative, for example, the fume hood, the cleaning stations, and the storage will be in close proximities of the glove box. And then that's to ensure like there's no way that lithium will be contaminated or get transferred to other locations. So it's pretty simple, and this is to be considered to set at the ESET buildings, probably on the mezzanine level, which is the blue colored regions. And we require about 1,000 square feet of the space, and that should be sufficient for the box and everything else. So, yes.
In the ESAT building, is this where there are two areas and they're below ground level? Is this where this is going to be set up?
No, this is above the ground level. So actually, this is the ground level, and you have a pit, which is the yeah.
So, but this is not in the pit.
This is not in the pit because there might be some flooding or water issues that you don't want to get.
So one minor point on this, you got this from Larry. For some reason, he's got that yellow area laid out. That doesn't exist. There's no.
I think the yellow is under the mezzanine.
Nothing. It's just dirt and concrete.
Okay.
There's no differentiation between the blue area and the yellow area. I don't know why he laid that out originally.
I took this from a previous design.
Yeah. I actually went and looked, and it's a wall, concrete wall.
Thank you. Yeah, we'll definitely use that regions if possible. Yeah. So if you're interested in the glove room design, right, I'll give you a little bit more details. Of course, this is prefab by the vendors, and then this whole thing can be built within about 4 months. So it's pretty quick turnover time. A few important components, for example, we do have an AC system for the box, right? So what this is, you have a circular blower, right, on the right, and then that blows the argon inside, recirculate the argon gas inside the rooms. And that goes through this heat exchanger, which acting as a chiller connected to a 10 kilowatts chiller outside. Of course, you have a more powerful chiller, you get better, cooling. That can cool down the argon gas inside the room. So this is for if you put a heat source or if you heat up the coils inside the room, you require some sort of heat cooling, and the air cool can be an option here. This is connected to the gas sample unit, which analyze the composition of the gas. Yes.
So these circulation blowers have a lifetime, and they need to be swapped out every once in a while. It might be nice to have a bypass blower when you want to do that.
Okay. Yeah, that's a good suggestion actually. When we talk to the vendor, they will probably help us design the whole blower system, and I'll mention that. Thanks. On the left side, you can see all the electronic box, the feed-throughs, that including the room air purge inlets. So whenever you're in the downtimes, you don't want it to run anything lithium. You push all the lithium into the dump tank, which is the storage tank inside the box, and turn off the valves, and you can purge the room with room air. So you can enter this. Of course, this is related to the oxygen sensors that control the doors and the access. Okay. For purging, we were thinking of different strategies, one of them being using the argon cylinders. And just because of the sheer volume that we're dealing with the glove rooms, it can be a little bit expensive over time. So another option is to use the liquid argon tanks that has about 20 times the volume of the cylinder per tank. Downside is outgassing a little bit every day. So we want to use this for purging events where you have to replace larger volumes and then replace about a few times of the box volume. And then for maintaining the pressure, you probably can get by with the smaller cylinder. Okay, so for the scientific missions, once this built, we're probably going to separate this into a 2-phase. The first phase is with working with limited lithium, and that's probably we're either try to prove try to make the loop works, or we can just separate the text sections from the loop and just focusing on a non-flowing, it's a closed system. Where you can just put something like a divertlets, which is a small sections of conductor into the leap test bed, which I'm showing on the right, and you can see, or observe the velocities and the temperature and heat transfer efficiency with the liquid lithium. And then the interesting thing about liquid lithium is that right now we do have a prototype with Galveston, and then Galveston does have a different material property with the lithium, and including different surface tensions, different density, and so all these can be further verified with a liquid lithium prototype, and actually build it to the size that can relevant to what the reactors or what the NXTXU or maybe the core edge facility would want it. In the second phase, when we have this full inventory of 50 pounds, that's when the building has been renovated, right? And then ESAT has been renovated and good to go for our LEAP system. Then we can turn on, then I can use all the volume up here and then to test some of the lithium hydride plumbing or heat and momentum transfer studies, right? For CPS lid channel flows that requires very high flow speed. If you put a asymmetric coils, you can study the gradient B effects, gradient magnetic effects on these lithium flows on the PFC designs. Maybe there is a chance that we can do in situ material analysis, that you put some lasers or X-rays and pointing at the surface and look at how the material change over time. Okay.
You said something about thermal conductivity or thermal properties. What sort of thoughts do you have for how to heat the surface? Power to the surface.
Right. If I have an infinite amount of resources, so I'll probably use E-beams and then plasma heatings. But if there are radiative heatings that you can kind of simulate the distribution of heat flux on the surface. In a least preferable case, but you still proof of concept, you can use a localized heat source like a heater. Like just focusing at one regions of your liquid surface. Yeah.
And I didn't fully understand phase 1 and phase 2. You said something about the ESAT building needing to be changed between phase 1 and phase 2, or?
Yeah, so the current plan is because the ESAT has, which I can show you some of the, there are the regions that were interested to put the device, for example, on the mezzanine, there are a bunch of frames that's been set it there, and then I think the facility want to remove them in a year or so. So they wanted to design, renovate the place, make sure the HVAC system is up to code, so we can put devices there. So the first phase we planned it to do is to build this prefab glove box, which is easy to do in a different locations in that ESAT. Right. So, and then once we set it up, we can use about 5 pound lithium and then do some of the small scale experiments, such as divergence. And when the building is actually finally up to code, then we will be able to bring the 50 pound. Okay.
Can I just say that, go back to the previous slide?
Yes.
I mean, you really ought to only talk about implementing a 50 pound inventory if you need a 50 pound inventory. Now,
that is correct.
I have not seen any designs at all which require anything close to that. So really, for some reason, 50 pounds seems to appear in these things all the time, but you need to justify that much lithium. It's a lot of lithium. And there will be a good deal of review of the systems inside the glove room.
Right.
Hi, Dick. Do you guys hear me?
Finally, hang on for a second. Finally, the last thing is you really need to, for 50 pounds, you need to think about what happens if there is a spill in the, well, how do you recover from it? So don't push for 50 pounds unless you really need it. is my advice. Is that, I figure that's Eggman on the,
Yeah. I mean, he can answer it as well, but let me just. So, I mean, for those of you who don't know, the main reason for this was there's a fine for safety wise. There's limits on pound, half a pound, 5 pounds, and 50 pounds. So once we knew that we need more than 5 pounds, so that puts you in the 50-pound safety regime. So that was the main reason we write this 50, because it's anything between 5 to 50 is kind of similar in some ways. In terms of that's the design of the enclosure itself. In terms of operational safety, it's a different, like you said, if I'm operating at 20 pounds and so forth, then it might be different than 40 pounds. So that is something we're gonna obviously look into. But the reason for the 50 is that once you pass 5 to 50 has the same safety requirements on the enclosure itself. So that's different than operational. Thank you. That was the reason why we always say 50, because once you go to 51, then you have to go to an even different safety procedure. Thanks.
Yeah, so I think that we do have the jurisdictions to determine that, in this lab, determine what is the maximum allowable quantities. And of course, we also have to look at the building code for that. But yeah, I think what Eggman said is valid here. I said the full inventory, it's not the eventual operational inventory. It's just something to look at. And if you develop a system, which I will show in a few things, just consider the elements and the components, you will see probably you need much larger than 5 pounds. Okay, I'm going to skip this. So this is just the main controllable parameters that I show here relevant to this system. And what you can do here is to use the non-dimensionalized parameters to scale what the lithium the lithium system inside the leap, and then how does that correlate to a larger B field? For example, if you just look at the blue, the dark black line here, the black line is basically change the Harman numbers change with the length scale inside the leap, and that correlates to a 10 Tesla B field with probably that has the same Harman number of 10 Tesla B field with about 5 millimeter channel. So if you develop something in a 10 centimeters size in LEAP, that correlates to the Harman number and the correct Lorentz ratios in a 5 millimeter in a much higher field. So LEAP can be used to simulate these small lithium flows at higher Harman numbers. And for open surface, we'll also have this will have a more realistic surface tension effects than Gallenstens and other proxies.
So you're saying that you can do a fully self-similar. You gave us all those parameters.
Yeah.
If you can't get 10 Tesla, you go to lower field and then larger size.
Exactly.
And that gets you all those different parameters. You have like 8 parameters.
Well, it will get to about the Lorentz force, and then you have the surface will probably be surface tension will be a little bit different.
That's what I was thinking.
Yeah.
And the Hartman force, the Hartman number, you can get the same, but there's all these other things, right?
Yeah, mostly surface tension, and the other ones probably not that relevant in terms of the size of the channel.
So you're conning us by showing us 8.
Yeah. Yeah, and then you can look at the Pacman numbers or Peckley numbers for how efficient the advections is compared to the conductions using the same tools. Then you can think about, okay, if you have operating at a few millimeter per second to 10 meter per second flows, how does that correlate, and then how much heat you can advect. So using the same tool, you can see the gray box is where the operating parameters for LEAP, and it's definitely a reactor relevant, I would argue. Okay, because of time, I'm going to skip some of the loop designs here, but the key takeaway point is that we do have all these plumbing system designs for the plumbings, the gas ventilations, electricities, and some basic drawings for all these designs. And we're currently working on the design reviews for these components. And hopefully by the first quarter of fiscal year 25 or end of this year, we can get to the design review. Okay, so yeah, these are the pumps that we have, the cold traps that we're going to use to reduce impurities in lithium. We have all the tools and designs and concept. Many of these has been proven and then calibrated and then work on other devices and other systems. I have to mention this as well. So this is developed, I think, 2014 in the lab by Jacob. And then this is one of the pipe joint leak detections that we can implement it on our system as well. Besides that, we have state-of-the-art diagnostics. We have laser profilers that you can see the surface dynamics oscillations over time. And we have Doppler probes, velocimetries techniques, which part of my PhD thesis. We have XRF, which is the machine that we have a handheld X-ray machines at Puro Lab that can measure high Z impurities. So if you're interested, definitely go to the poster section. We have SULI students work on this. And we have free MHD in-house, the free MHD code to simulate all the MHD flows, incompressible MHD flows in different complex geometry. Okay. So last things, this is probably a takeaway message, is that maybe in my wildest dream that Leap can be acting as an interface to fusion facilities. It can be a decentralized lithium distribution system where you have this, because the panels are fully customized and modularized, you can make it mating to the channels or the chambers of the fusion device. And it can be a real-sized modularized system for fusion reactors, just as is. And of course, if you add multiple of them around the reactors, it gives you engineering redundancy and ensure the safety operation of any lithium components or liquid metal components that are required for the PFCs or limiters or any first world components. Okay. Yeah, some updates. And then I really appreciate all the helps and guidance from the design committees. So I'm not going to read all the names here. But thank you very much for all the help. And thank you very much. So for conclusions, we have important, LEAP is important for this prototyping, and then we have this designs, and then this is a potential novel integrations with fusion reactors. Thank you. Yeah.
All right, I'm going to start with online questions first. So Bob, why don't you go ahead? You're muted.
So very nice talk, Yufan. These are not really questions, but some comments just from past experience. The first being that too many years ago, I worked with Sid Medley and Lane Mokmore on a test stand on the platform in the ESAT building. And I don't know what the sequence or the status of the ESAT building is now, but there's a lot of room up on what you might call the mezzanine or the ground level. And so I think that if properly cleaned out, I don't think that even without doing anything to the pit, that shouldn't be a problem if that's anybody's concern. The other thing is that then with that schematic that you were showing, with the possibility of several modules that we've talked about that are around the machine, one of the things is that you can do a lot of testing, to refer to the previous comments about keeping the lithium inventory low, that I kind of agree that you may not need the 50 pounds. But at the but what it says is that you can use smaller quantities in each of those modules. And also too, when you think about the total inventory, it's not the total inventory in each of those modules, but the total inventory inside the machine. And you could take credit for what the machine provides in terms of protection against lithium. So I think that's another idea that then is attractive about this modular approach, because then you could go ahead and do all of these studies on a smaller level that would be really prototypical of what you're going to put on the machine. And the final comment is that I'm glad that what you're doing is, maybe it's obvious, but what you're doing is that you're using the electromagnetic induction pumps rather than the inline impellers, which are a real mess. And that's what Mike Jaworski bought many, many years ago. And that, together with the protection of each of the plumbing systems, all the joints, that was also developed at that time for that lithium loop. At least I feel pretty good about what looks like a decent design that should quell any operational and safety concerns. So those are my comments. So yeah, good design.
Thank you, Bob.
Rich, go ahead.
Just a couple of questions. The first is, are these units something you can buy commercially, such that they're essentially turnkey type units that you can get delivered?
For the glove box, yes. So all these designs you see is actually we're working with different vendors. For example, this one is manufactured by Embron, and then we're just getting some preliminary drawings, and they can build the box in like 4 months or like 20 weeks or so. So it's a relatively short time scale on their side, and then we have the freedom to sort of customize it as we wish. So which is one of the attractive point of this design, that we don't actually need to build everything on site. For the loop, we will probably design it here, and then most of them is the simple pipings you can buy off the shelf, and then the valves and all these components. If we're using the permanent magnets at first stage, this also something coming from the manufacturer that you can buy it. So yes, we're assembling everything, and then we design it in-house, but we're not technically building everything.
Okay, very nice. Second question, going back to something that Dick mentioned, is the amount of lithium. I think what you need to do is a very comprehensive failure modes and effect analysis, that if something fails, you have lithium all over the place. What happens then? How do you clean it up? How do you I think what you have something here is just going to be safe, but you still have to show that the number of barriers are not compromised, and then you do have a path forward as far as cleanup and dispersal. That may be something you have to do in the future, but if it hasn't been done yet, something that probably you need to put on your list.
Yeah, thank you. We have considered this. I mean, the whole idea of this is the secondary confinement, which is in case of the catastrophic failure of the first layer, if you have a molten lithium coming out of these pipelines, the whole box is made of stainless steel and with the definitive depths at the bottoms, which can definitely have enough thermal mass to stop lithium from reacting further. But that basically will make sure that it will basically cool downs and solidify the lithium. And of course, this is also in the inert environment. So you're not going to have exposed air or water when the lithium is, for example, leak out of the pipings. For cleanup, of course, these are procedure things that we'll have a better ideas when we get to the finish lines of all these design reviews. I hope I can give you a better answer then.
Well, just to follow up on what you just said, which I think is reasonable, let me begin with that. Even if you have a secondary barrier, you have to evaluate the probability of that secondary barrier also failing. And if so, what the consequences are.
Yeah, sorry to interrupt. From the pressurized vessel code, if you also consider the secondary barrier failure, that's like double jeopardy. So usually it's not being recommended in the engineering design, because this is just an infinite loop, right? What if the third barrier fails? What if the fourth barrier fails?
It's a question of probabilities. If the probability, your argument is that the probability is low and it's not a problem, and you may very well be right, but that's what you have to look at.
Yeah, we'll think about it. Yeah. The design review chair said no, so.
I'll just point out, we've always worried about the secondary failures. The primary barrier, for example, for lithium and LTX is the shells. The secondary barrier is the vacuum vessel. And so we've worried about, what happens if we do spill, and we have had in the past, years ago in CDX, cases where the primary lithium filled limiter, for example, ended up leaking or wicking lithium onto the vessel. And so it is And after all, if you think about the Sandia experiment, what happened was the primary containment within the pressure vessel failed. And as a result, lithium ended up contacting a very, a surface which wasn't resistant at all to lithium. And so that's the kind of failure we will have to worry about.
I would argue Sandia is a different type because
Yeah.
you do have components we're not going to put it inside the primary. But yeah, we can have the debate later.
Yeah.
Bob, yes, you raise your hand.
Yeah, I think to echo the point about what is considered good engineering practice for this, you also have to be careful. I agree that you don't get into this kind of infinite loop situation, because one of the situations that we had to account for NSTX in terms of the lithium dump system, or the argon purge system, was to have the incredibly improbable but the instantaneous failure of the leaders, which was a welded stainless steel container, which is not, by the way, like the ferritic steel that was subject to the kind of embrittlement that that was described. That then was a sequence of failures that caused the problem in Sandia that Richard Nygren analyzed in excessive detail. But we assume that then all of that lithium from that spontaneous evaporation, if you will, of the leaders would then dump all of its lithium onto a single tile. And then on that single tile, taking no account for the thermal mass that the lithium was going to fall on that single tile, with then the simultaneous ingestion of air into the system, that tile would combust. And so Bill Blanchard and I didn't complain about it because he got a free, if you will, argon purge system that was automatic that he always wanted. But this is to make the point that maybe I don't want to belabor this, but the kind of analysis that needs to be done should be cognizant of good engineering practices and also cognizant of laws of physics. So we could talk about it a lot here, but I think that all of these things are going to be considered, I'm sure, in the final design of the box.
Yeah, thank you. Thank you for the comment.
Rob, you have a follow-up?
A little bit. You had the picture with at least two leaps.
Yes.
Sitting around NSTX. So that brings up the question: what do you think the inventory of the whole lithium system, if you had a full toroidal system of divertulets and everything else, and how does that's a first question. What's the total inventory we're talking about? Is it 50 pounds times 4 or something? Or
so it's I can't give you an accurate number, but I can try my best to reason this. I would argue that because of the redundancy, right? So we want each system to actually house at least, not fully all the lithium inventory, but maybe almost all the lithium inventory, just in case, let's say 1 or 2 boxes failed, and you will be able to flush all the lithium into one of the glove box. And that being said, if you think about the size of the divertulets, which I think I showed here,
piping and everything.
Yeah, without the pipings, you're looking at probably 3 centimeter, 2 or 3 centimeter, and with the 5 millimeter width of channels around the surface, if the radius about 1 meter, then you are looking at 3 times 0.003. So
got to go all the way around the torus.
Yeah, all the way around the torus divided by, I guess.
But it sounds like you haven't done that calculation.
Yeah, I haven't done it, but
while you're standing there.
Yeah. So, but I assume it's not a lot if you're just replacing the tiles, one of the bottom tiles. But you have to count for the plumbing system that you have to fill the pipings, and that determines by the total length of it and also the diameter of it. Yeah, you don't want it to be too thin, so you can have clogging by lithium hydride, which is a solid. But yeah, it will be great. I haven't actually ventured on these ideas further, so I just put it out first time for this talk. But I'll probably, if it's interest to everybody, I can go down this rabbit hole.
There's also the funny issue that NSTX is pulsed, and so the field will go off.
Yeah.
And so how does that interplay with how the how the diverter are working? It seems like it's a funny. I mean, in some ways it's a harder problem to do a pulse machine, but it seems like it's important to think through where we're headed with this, how we're going to make that whole system work.
Yeah. All these concepts, divergence requires you have a substantial background toroidal field. So without the field, you won't be able to. You can probably drive the flow from the flow is fast enough from the induced field, but something like I think something like a very stable operation of the divergence does requires you have a steady state background field. That being said, by plumbing, we have moving magnets pump, which is a large pump. It's a large spinning wheel permanent magnets that's non-contact with the liquid metal. So that provides a pressure drops pretty consistently and constantly. So that can at least transport the lithium in and out without the interruptions from the B field. Yeah. Okay.
Other questions? Yeah.
How are you getting your argon, the liquid argon you mentioned? Is there a vendor that just gives you tanks?
Yeah. You can. There's a on-site supply that we have here, but we can have like ultra pure argon as well. Yeah.
Wait, we have an on-site liquid hydrogen or liquid argon supply?
Not liquid. I think bottled.
Oh yeah.
Yeah.
You're asking about liquids.
Are you asking about liquid?
Yeah.
I haven't looked into it, but I'm assuming they should be able to deliver if they wanted to. Yeah.
The reason to ask is when we run our liquid nitrogen in surface science lab, one of the radiation labs maintains a liquid nitrogen reservoir that we just wheel the tank to and refill, and that's very convenient. I was wondering if there's something like that.
Liquid argon colder than nitrogen?
Yeah. Liquid argon is more expensive, I think.
It's more expensive. It's warmer than nitrogen.
It's slightly warm. Yeah. Not by too much, but maybe you can use liquid nitrogen to cool liquid, to cool pressurized liquid or
Just
pressurized.
make it yourself, pull it out of the air.
Yeah, all around. And then are there talks about adding more diagnostics? Like, I think D3D is procuring a handheld LIBS system, for example.
Oh, I'm sorry. What?
There are plans. The PPPL D3D group is planning to acquire a handheld LIBS system, that's laser-induced breakdown spectroscopy. You can make a similar kind of diagnostic out of that for your point liquid lithium groups, except it would be slightly more surface sensitive than XRF.
Interesting.
Also, you can see hydrogen with that, so you would be able to determine if you have hydrides or not.
It's off the order of $30,000 or $40,000. But
Were you gonna have a nitrogen scrubber?
good point.
Good point. This is also for the secondary confinement. The first confinement will keep the nitrogen concentration below
Yeah.
1 ppm or so. But I think for adding nitrogen scrubber is really expensive.
Yeah, you don't need that unless.
For the whole glow room, it would be very expensive.
For the what's the environment in the inner glove room again? The inner part that's around all this stuff. The first.
That's a vacuum.
Oh, you mean the loop?
Yeah, loop.
The loop, you can, so two modes. You can operate on the vacuum. Probably valve system. Yeah, you can operate on a vacuum, so you can see there's a vacuum attached to it. Or if you turn that off, you can flush the whole system with argon. So you can do argon pressurized surface.
So in some modes of operation, the diverter, let's say, for example, would be running under vacuum.
Yeah, it can be. And it also can be running under argon. Depends on the heat source we have, right? If you have an E-beam versus if you just want to use a torch, that's different. But again, I think the key point here is the magnetic regions, the channels here, it's interchangeable. So if you want to change your study, or if you want to just focus on the closed loop, or versus you need some diagnostic, we can probably modify this, and then everything else will be the same.
Bob, did you have another comment or question?
Just two really short ones. Just a historical note. That scheme that was from 2000 assumed that between shots, what you do is we filled out a reservoir and then let the lithium just run through. But I admit that the force flow issue is still yet to be resolved and further discussed. And that was really the main thing I wanted to mention. But yeah, I think that there's nothing fundamental, I think, in any of these problems that's at least potentially not solvable. So that's all. And again, good talk.
Any other final things? All right, let's thank Yufan again.
Thank you very much.